Picture this. A Ukrainian pilot climbs into a Soviet-era MiG-29, knowing he must carry American-designed bombs deep into Russian airspace. Every step is calculated, terrain masking at low altitude, threading through radar belts, and waiting for the exact second when defenses are stretched to their limits. For the next 90 seconds, survival depends on perfect timing, flawless technology, and nerves of steel. What unfolds inside that short window becomes one of the most daring precision strikes you'll see in this war. How can a 40-year-old MiG push through one of the most layered defense networks on the planet without being torn out of the sky? That is the question the men preparing the jet on the tarmac had to answer. The MiG-29, born in the final decade of the Cold War, was never built for this exact type of mission. Ukrainian ground crews moved in tight coordination, checking and rechecking each system on the aircraft. These were not routine checks. Every wiring harness, every pylon, every coupling mattered. The aircraft had to be reconfigured not to carry Soviet ordnance, but American-made precision bombs. The stress fell on both human hands and outdated metal. If anything failed, the jet would never return from the mission it was about to undertake. The task was harsh in its simplicity. The fighter needed to carry GBU-39 small-diameter bombs into skies where radars overlapped like nets. These weapons were compact but heavy in impact, designed to glide for long ranges with guided precision. Yet attaching them to a Soviet fighter meant bridging two very different design philosophies. Where the MiG relied on raw thrust and agility, the GBU depended on satellite correction and onboard computers. Now both had to function as one inside an area flooded with hostile countermeasures. Russian Kushuka-4 jamming systems, stationed tens of kilometers inside occupied territory, filled the spectrum with interference. Each system could output up to 500 watts directed at navigation satellites. That level of power was enough to corrupt GPS reception in a broad radius, forcing any munition that relied solely on satellite guidance to wander aimlessly. For the pilot watching his systems, that meant instant uncertainty. Flight instruments blinked in and out. Heading indicators shuffled backward, then righted themselves. At one moment, the autopilot compensated, at the next it disengaged. At this altitude, the only shield against detection was terrain. The pilot ran the jet low, hugging folds in the ground, using hills and ridges to block radar line of sight. The danger of flying so near to the Earth meant a single misjudged correction would smash the aircraft into the soil before a missile ever found it. The cockpit environment reflected the strain. The altimeter pulsed rapidly, speed numbers ticked higher and lower within seconds, as turbulence gusted near the ground. Inside the bombs hanging from the pylons, systems were running their own calculations. Their inertial navigation assemblies measured acceleration and direction approximately every 20th of a second. This constant measuring provided a backup layer. Even when GPS signals distorted, the onboard gyros and accelerometers tracked where the bombs were traveling, recording movement almost like a heartbeat. This hidden insurance reduced circular error to a margin of about a dozen meters, even under heavy jamming. As kilometers closed, the workload magnified. Russian radar coverage did not thin. Instead, each belt brought new frequencies, new scan patterns, and denser cross-checking among operators controlling separate systems. For the MiG-29, the window to remain undetected narrowed further. Fuel consumption ticked against the clock as low-altitude flight drained more kerosene than cruising. The pilot's oxygen drop mask pressed heavier on his face as he focused his vision on instrument clusters, jittering under interference. He had committed, and the point of release was approaching. In these conditions, the old jet proved more adaptable than expected. Its simple airframe was not meant to carry Western glide bombs, but the grafting of suspension racks, interface modules, and software patches turned it into a workable platform. Fragile in theory and practice, it became the only airframe available to carry them across this hostile belt. Against cold metal and scrambled numbers, human skill and engineering adjustments held the MiG steady on path. Now the jet sat perfectly threaded between radar zones. Computers linked, targeting confirmed, the bombs armed in sequence beneath the wings. The stage was set. The release window, only 90 seconds long, had begun. What happens inside the final 90 seconds before a bomb leaves the wings of a fighter jet? For the MiG-29 rushing toward its strike point, These seconds are not just a routine part of the flight plan. They are a countdown where every moment can be the difference between success and being shot down. At this stage, the aircraft has threaded past radar barriers, descended under jamming, and now hovers at the outer edge of the engagement zones of some of Russia's heaviest air defenses. The critical piece is that the MiG no longer has the flexibility to turn back without losing the strike, so the only path is forward. Time is now measured in seconds rather than minutes. The strike position lies inside the overlapping envelopes of S-300 and S-400 surface-to-air batteries. These launchers are optimized for high-altitude targets, but their radars can still track fast, low-flying objects if given enough time. Layered under them sit the SA-15 systems, designed to swat down glide bombs, drones, or even cruise missiles before they reach impact. It is against this entire suite that the MiG must complete a perfect sequence, releasing weapons and escaping before lock-on is confirmed. Any delay in timing risks drawing interceptors or triggering missiles already queued for launch. Meanwhile, the electronic fight is already underway and visible on both sides. Russian radar dishes sweep the air with beams measuring course and velocity. Operators compare tracks, trying to determine which faint echoes belong to decoys and which indicate real intruders. In response, Ukrainian electronic warfare units flood the spectrum with deceptive data. They generate phantom signatures of aircraft hundreds of meters away from the actual MiG, forcing radar trackers to split attention across multiple false trajectories. For the Ukrainian pilot, these efforts buy only moments, not minutes. The aircraft must reach its point and deliver before the confusion clears. The bombs themselves handle their own battle against interference. Attached below the fuselage and wings, each GBU-39 runs guidance software that can switch seamlessly between satellite correction and inertial navigation. When GPS reception thins, circuits inside the bomb rely on onboard gyroscopes and accelerometers to project the flight path. Even under sustained jamming, the error rate stays low, keeping accuracy within a dozen meters. This margin makes the difference between missing a hardened factory wall and striking at the joints of the structure. Release geometry has already been calculated so that when the bombs separate from the MiG, they fall at an angle of 68 degrees. This angle allows the weapon to carve deeper into reinforced surfaces before the charge detonates, maximizing penetration rather than producing a shallow explosion. Matching distance, speed, and pitch with that steep approach requires precision piloting. Any deviation widens error, forcing the bomb to contact less critical areas. For the pilot, there is no opportunity to improvise. The aircraft must align exactly with pre-planned coordinates while still under threat of radar detection. At release, 4 bombs split from the pylons. Each is programmed to veer toward a separate facility. Their tail fins deploy, and they glide independently under the guidance system's corrections. From the ground, Russian operators scramble to update fire control calculations, but the weapons are too fast in their final dive. One strikes the electronics workshop's roof, imploding the thin frame and scattering circuitry across the floor. In less than half a minute, the drone supply line suffers a decisive fracture. What remains are smoldering structures, equipment beyond repair, and disrupted logistics. The event demonstrates on a wider scale how a Soviet-built fighter, altered with modern hardware, can execute a strike that fuses outdated airframes with contemporary precision arms in a way that neither could achieve alone. This fusion now defines the next phase of aerial warfare. The strike showed that an aircraft designed decades ago could still punch above its weight when paired with modern weapons built to withstand electronic interference. The MiG-29 was not a cutting-edge stealth jet, yet once linked to Western precision bombs, it became a serious threat to fortified targets inside defended airspace. What this combination proves is that technology does not need to be new to shift the balance. If outdated platforms can disable drone production today, the next step will be how such mixes might expand long-range attack options tomorrow. This mission was more than destruction, it was a preview.